So we begin a little bit later. I'm sorry. I try to put things to avoid the longer formula to write on the blackboard. So, okay, now in the previous two lectures, I have essentially laid down the motivations of quantum probability. So you have seen that starting from classical random variables, you associate a non-commutative structure canonically coming from the random variable. This non-commutative structure is the algebra generated by the creation, annihilation, and preservation operator canonically associated to the random variable. So this algebra usually will be an algebra of unbounded operators. But we know that there is a natural domain for this unbounded operator, which in the example of classical random variables is given just by the action of the polynomial onto themselves. So since our pre-Hilbert space is the algebra of polynomial, of all polynomials, then this domain is dense by definition in this pre-Hilbert space. So this justifies the first definition that we will give. I have tried to avoid to reduce definitions to a minimum, so you immediately get to the basic ideas with a minimum of notation. However, a minimum of notation is necessary. So we define an algebraic probability space. This will be our context from now on. But in a moment, you will see that, in fact, in this lecture, the context will be even more general. However, what we constructed in the previous lecture was what we achieved in the previous lectures was to show that to every classical probability measure on R, or in fact on RD, with all moments, it is canonically associated a pair where A is a star algebra and phi is a state on a star algebra. By star algebra, we mean an associative. All algebras will be complex unless otherwise stated, and all algebras will have identity unless otherwise stated, and an involution. This additional technical condition on the star algebra we have put to avoid, because if you take two general star algebra, you can have a lot of pathologies, okay? So to avoid at least some of these pathologies, we have put this condition. Phi is a state on A. Remember, the positive elements of a star algebra are the sums of elements of the form are the sum of elements of the form x star x, and if star algebra is a topological, also the closures of such elements, and the limits of such elements. And the algebraic probability space is called classical if A, the algebra, is commutative. And it is called quantum if the algebra is non-commutative. We will see several examples, several important examples are given by C-star probability space, in which the algebra A is a C-star algebra. Another class will be given by the W-star probability spaces, in which the star algebra is a von Neumann algebra. And in this case, we will always assume, unless otherwise specified, that the state is normal. Normal means it is a general theorem of von Neumann algebra that a normal state is a strongly continuous or ultra strong or weakly or ultra weakly and so on. let us do some example to show you something that will come later. Basic examples are classical ones. Then we will introduce many non-classical examples. But I want to show you the differences between that why we will choose certain equivalence relations. So the basic example are this. You can take, if you have a probability space, a measurable space and a probability measure on it, you can take as an algebraic probability space the algebra of finitely many-valued test functions defined on the probability spaces with complex values, and the state will be given by the integral. This is an example of algebraic probability space. If you take the L-infinity function modulo the the functions which are defined on a whose support as p measures 0, then you get an example of W star probability space. And if the space omega is a topological space and the algebra A is the algebra of a continuous complex valued bounded functions on this topological space, then you have an example of C star probability space. I want to draw your attention to the fact that all these three probability spaces uniquely determine the probability measure. So you understand that I can have probability space with algebras which are very far from being isomorphic, but which define from the probabilistic point of view the same measure. Given any probability, any algebraic probability space, we will define the cyclic representation. Cyclic representation is the C star algebra analog of what is called GNS representation. In fact, it should be called the Kolmogorov representation, because the first person who really understood the essence in even much more generality of this construction was Kolmogorov in his study of infinitely divisible functions. So this is to fix our notations. We will mainly work on pre-Hilbert space. There are some reasons to prefer pre-Hilbert to Hilbert, as I explained to you last time. And when we speak of a linear map between pre-Hilbert space in our notation means, first, that there can be elements of zero norm. Second, that the space is not necessarily complete. Okay? So it means two things. A linear map of a pre-Hilbert space is a map that preserves the subspace of zero norm vectors. And we will use these notations. We call L of A, this L of A of H means the adjointable operators defined on the Hilbert space. So by definition, these operators leave the pre-Hilbert space invariant. Okay? This is very important. This avoids to put from outside invariant domains. And B of H, we denote what they will become the morally, in the Hilbert space will become the bounded operators. Okay? So they are operators which, when I quotient out, they become bounded operators. And then we define the notion of representation. Representation of a star algebra is a star homomorphism. So an homomorphism of algebra which commutes with the involution. And so we have the notion of representation, which is given by a pair. So given such a representation, we define the commutant of the image of A for this representation to be the family of bounded operator which commutes with the representation. So you see, by definition, the commutant is made up of bounded operators. And because of our, even if the representation itself, the P of A, may be unbounded operator, because of our condition that the Hilbert space is the pre-Hilbert space is preserved under the maps in questions, we have that this identity is always well defined. That is, here is obvious because X is bounded and P of A is defined on the pre-Hilbert space and maps the pre-Hilbert space into itself. On the other side, the right-hand side is also well defined because X maps the pre-Hilbert space into itself. And the operator P of A is, by definition, defined on the pre-Hilbert space. Usually, this would not be true on general unbounded operator. So, by definition, the bicommutant of P of A is a subalgebra of bounded operators. So, does not necessarily include P of A itself, as it is unusual for Neumann algebra. This is a simple lemma that the proof I will skip because it's very standard, that if you have any pre-Hilbert, any pre-Hilbert space, is not a this is an error, not an algebraic probability space, any pre-Hilbert space, then the ideal of norm zero element is then the set of norm zero element not only is a subspace, but is a left ideal for the representation of A, left regular representation. I don't give you the proof. It is written here. The only point is that you want to. The only point that is interesting is that what replaces the boundedness condition in the usual GNS representation is the Schwarz inequality. That is, you want to prove that it is an ideal. So if I multiply X is a norm zero element and A is an arbitrary element, I want to prove that it is still. And here we use the algebraic analog of the fact that the measure is moments of all orders. You see, that is a delicate. In this lecture, for us, a random variable will be an element of the algebra. But this is not a good definition of random variable, because this automatically will exclude from the, if I have an algebraic probability space and I have an element of the algebra, then by definition of algebra, all powers of these elements are in the algebra. And therefore, the state is defined on all powers. So if we accept to identify the element of the algebra with a random variable, we are losing a lot of classical probability. That is why our definition in the future of random variable will be more general, okay? But for the lecture of today, we will restrict to this kind of random variables, and we call them operator random variable. The operator random variables are the analogs of random variables with moments of all order. And this is the cyclic representation. Now, algebraic probability space here is correct. If we have an algebraic probability space, then we repeat, generalize to star algebras, the standard GNS representation, and we obtain what is called and we obtain a representation with a cyclic vector. Cyclic vector means that the image of this vector under the action of the representation P phi is dense in the pre-Hilbert space norm. Again, I don't, and this representation will be called cyclic representation. I don't use GNS to emphasize that we are speaking of star algebras and not C star or W star algebra. Now we come to the delicate point that I try to anticipate in the beginning. When you define some mathematical object, you should define what are the equivalent. Otherwise, it's not well defined. You should define a category. And so what is the category of algebraic probability space? The equivalence relation is not completely trivial, because you say that two algebraic probability spaces are equivalent if their cyclic representation are unitarily isomorphic. So there is a unitary operator, unitary isomorphism, between the space H1 of cyclic space of this representation and cyclic space of this representation, which intertwines the cyclic vectors, and with the additional property that if I define the star homomorphism given by this is a star isomorphism at the level of all bounded operator in Hilbert space. But I want that the restriction of this automorphism, in fact isomorphism, on the bicommutant of the first algebra is a W star isomorphism onto the other algebra. Why this is needed? Because if you remember my original example, I had in the classical case, I had three completely different algebra. I cannot require that the isomorphism U brings an algebra into the other. This is too strong. It's not verified in the elementary classical examples. So we need this condition, which is weaker, and which is called, in the theory of von Neumann algebra, is called algebraic isomorphism, not quasi-equivalence. Algebraic isomorphism. Of what? Quasi-equivalence. Of? Quasi-equivalence. Isn't this quasi-equivalence? This is the definition of equivalence of algebraic probability spaces. You see? In usual von Neumann algebra, when you have many notions of equivalence. You have unitary equivalence, you have algebraic equivalence, you have quasi-equivalence, and when you have von Neumann algebra with a state, you have equivalence intertwining the state or not intertwining the state, and when you have cyclic representation. Quasi-equivalence means that the representations are intertwined. So we have algebraic probability space A1, Phi1, A2, and Phi2. So we have the corresponding cyclic representation, H1, Pi1, Phi1, and H2, Pi2, Phi2. So the quasi-equivalence relation, which is very often used in the von Neumann algebra, is that this is in fact unitary equivalence, is stronger than quasi-equivalence, is that UH1, there exists a unitary isomorphism which intertwines the cyclic vectors, and when you define so this is U, and when you define the unitary isomorphism, which to an element, let me say capital A, belonging to the bounded operator of H1, it will associate U star capital A U. So this I will define like the unitary isomorphism U of A. And this is defined on all B of H. But of course, it's not necessary that the image of this algebra by the restriction of this isomorphism will be contained in the image, say, this algebra, will be contained in the image of this algebra. Because this is true for only at a bounded operator. This is bounded operator on the Hilbert space H2. So this is, it usually is not true this. But I require that this is an identity. This is algebraic isomorphism. Okay? Quasi-equivalence is much, much stronger. It means that the two representations are intertwined. U of P1 is equal pi 2. But this we cannot ask for standard probability space because of the three examples I brought in the beginning. The step functions are very far from being isomorphic to the continuous bounded functions. Yet they uniquely define the probability space. The standard equivalence for classical probability space is that you have a sigma algebra homomorphic, but the sigma algebra involved is the quotient of the sigma algebra by the null zero set, the zero set of the two measures, okay? So this is a little bit complicated to explain. Algebraic language is much more elegant.
What is the correct generalization of mutually absolutely continuous?
Yeah, this is also possible. Is simply that you don't require you simply require that that you don't require this condition. You don't require intertwining of the state. You simply require this. This is the simply equivalent to say, because the von Neumann algebra is the quotient by the zero vectors, okay? So it's...
That is saying that both measures are same.
Yes, yes. But I give only the stronger. I spoke of isomorphism. This is a refinement that we can discuss also later. Okay? It's a good question. Yes. So it's clear what is the answer. The answer is that, Okay. So this is the notion of isomorphism. I just put it because of theoretical reasons. We don't use it very much because we stick to a single representation in the central limit theorem. But for theoretical reason, it's important to have clear ideas. Now, what I want to do today, I defined the notion of algebraic probability space. But today, what is the main goal in my lecture is to show that one of the basic results of classical probability, which are the laws of large numbers and the central limit theorems, have a purely combinatorial root that is much, much, much more general. It has nothing to do with probability. So I will not assume positivity, which is characteristic of probability measure. I will not assume star algebra. I will assume algebra. I need multiplication because we will work with moments. So we need multiplication. We need algebra. But, you see, so we will drop these three assumptions. First of all, we don't need that the expectation is a complex number. What does it mean in the probabilistic interpretation, this? It means that the central limit theorems can be done also for example, for completely positive maps, for conditional expectations. But we say that we don't need positivity, so we even don't need complete positivity. You see? I want to emphasize this point because in classical probability, central limit theorem for maps are not so well known. But when you do algebraic probability theory, you see that that you can obtain such theorems practically without additional effort, at least in the framework of algebraic probability theory. So, what is the general framework I want to discuss? I will discuss in this lecture, which has to do with the basic result in the central limit theorem, the main estimate. The main estimate on the central limit theorem will assume that it's an algebra, but we don't need star algebra, we don't need identity. We have a normed space which will replace the complex numbers. We have a countable set. Typically, in the standard central limit theorem, this countable set is the set of integers. We have a sequence of random variables. But as I told you in the first lecture, my goal is to deduce the quantum fields from central limit theorems and functional central limit theorem. Quantum fields need multidimensional index set. Moreover, in recent years, there have been a very nice development of classical and quantum probability on graphs. In this case, the set V of index set is a graph. The simplest example of a graph is a lattice, and this is very widespread in statistical mechanics. Spin chains are defined on lattices, typically. But there are now many studies in statistical mechanics, for example, of spin chains on Cayley trees. And this is an example of a graph which is not a lattice. Okay? So, we have a normed space which replaces the complex number, and we have a linear map. For every finite subset of the index set V, we have a linear map depending on n. This is important because some central limit theorem require it, from the algebra A to the Banach space C. Then we have a set D. What is this set D? Roughly speaking, the set D is the index of the if you consider a vector valued random variable. In algebraic probability theory, essentially all interesting random variables are vector valued. For example, you have seen in the quantum decomposition of a classical random variable that even if I start with a single classical random variable, then I associate to it three operators: creation, annihilation, and preservation. So I need the three indices. If I want a central limit theorem, I need to take care of these three operators. Okay? If I want to include the classical central limit theorem and to express it in terms of algebraic, of quantum decomposition of the classical random variable, I will need that this set D has three indices. The index minus for the annihilator, 0 for the preservator, and the plus for the creator. And this will be our main example. Okay? In fact, our main example will be many, many famous central limit theorems are only with two indexes, which will correspond to A plus, A minus. So this is the interpretation of the set D. So, since we have no positivity, no state, no algebraic probability space, it makes no sense to speak of processes and of random variable, but we will use this terminology to keep intuition. So, when we have this sequence, the intuition is that these sets are the generators of a certain algebra. For example, in the 2 by 2 matrices, typically this set is the set of Pauli matrices. Okay? So you have to think of the Pauli matrices, sigma plus, sigma minus, and sigma 3, which correspond to creation, annihilation, and preservation operator. Okay? So typically, this will be, and so we call them operators, but of course in this general context they are not. And let me explain. The most important central limit theorem, the Gaussian central limit theorem, we will have that En will not be dependent on n. But if already you go to Poisson's central limit theorem, the expectation value will depend on n. So that is why we use this more general framework. Now we want to state the problem. What is the problem we want to study? We give alpha, which is a positive real number. Remember, S is the index which intuitively labels the components of a vector-valued random variable. Okay? So, for example, classical case x1 to d, we will fix this number, and it will be, for us, will be finite, which means an algebra with a finite number of generators. Then, okay, I will define in a moment this subset n. The subset script n in classical probability will be the subset of intervals. Because in classical probability, you consider sums of random variable from 0 to n, and we replace this by a finite subset of the index set. And the bar here means cardinality. This is the cardinality, for example, finite volume in statistical mechanics. So we define the normalized sum with the exponent alpha. And if alpha is equal to 0, so we only consider the sum, we simply write Sn. So we have this family. Notice that here n is the sequence, is the index of the sequence. Because the set of index v for us is always countable. We take a countable graph or countable set. We don't use the graph structure in this level. This index is the index of the component of the random variable, the vector valued random variable. Now, the analog for a general subset or a graph of this will be a filtering increasing set. Filtering increasing means that if you have two elements of this family, the union is contained in some subset of the family. This is filtering increasing. And absorption of this family absorbs all finite sets, which means, like this sequence of intervals, that if you take any finite set, if I take n large enough, it is contained in the interval 0, n. Okay? And this means absorbing. And so we use this notation. Limit for n increasing to v, absorbing all finite subsets, is equal to x. It means that it is convergence with respect to this net. Okay? Of course, this has to be meant in the topological sense. So the goal of the asymptotic theorems of classical probability is the one that we want to generalize here. We want to study the asymptotics of the normalized sums for alpha being at the moment a positive integer. We will any positive real number at this moment. So we want to study the asymptotic behaviors of expectation values of these sums, of products of these sums. That is why we need algebra structure. So if we take alpha equal to 1, we get the law of large numbers. If we take alpha equal to 1/2, we get the standard normalization of central limit here. You will see that for this way of stating the problem, no other possibility will be allowed, because we are considering convergence in moment sense. The more general normalizations appear in probability theory when you discuss so-called triangular arrays and you consider characteristic functions. So these, what we will discuss, to be precise, are not general central limit, but so-called moment central limit. Okay? Moment central limit are enormously general. If you want to speak of true central limit, then you have at least you must have the possibility to speak of characteristic functions. And so you have the possibility to exponentiate, to have unitary, to exponentiate sums of random variable, okay? Which is not possible in any, even in any sister algebra, because usually you have not convergence in norm, okay, of the exponential series, okay? So, using the linearity, you study the asymptotic behavior of polynomial. And using linearity, you reduce to monomial. So, essentially, we will reduce to monomials, but non-commutative monomials. This is very important. See? Let us do some example. The law of large numbers, as I said, in the law of large numbers, the normalization is 1. So, this is not section, sorry, I have a misprint here. So remember, we have this family, this is our family, in which the index where we sum is n. Then we say that this family satisfies the law of large numbers with respect to the given family of expectations if, first of all, this limit exists. This corresponds to the simplest possibility of the limit. But the non-trivial point is that this limit essentially will asymptotically factorize. This is the notion of large numbers. Let me make the connection with the classical probability theory to explain to you why this is really a generalization of classical random variables, of the classical law of large numbers. So, as we have said, convergence on monomials by linearity is equivalent to convergence on polynomials. So you see that if the family satisfies the law of large numbers, then for any polynomial q, you see, the crucial point will be here to exchange expectation and polynomial. Because polynomial is a nonlinear function. So, you see, the law of large numbers will be equivalent to convergence of monomials. And since we are assuming that for k equal 1, there is convergence, this will be the correct formulation for monomial. Pay attention, when I speak of non-commutative monomial, it means that this k can be much larger than the cardinality of d. So when this index S1, Sk, will be, in general, this index S, you can consider it as a function from 1k to the set D. That is the set of, remember, the components of the random variable. But we are in a non-commutative setting. So if k is much larger than the cardinality of D, many indices in this form will be repeated. In this product will be repeated. If everything commutes, you have powers. But if not, you have a notion of non-commutative monomial. Okay? Another interesting remark is the following. We have said that this, for the single sum, we have always the limit by assumption. And so the limit, we will, for the moment, denote like an expectation value. If you think of the BS as the generators of an algebra, for example, the algebra of 2 by 2 matrices, then since the generators are algebraically independent, not only linearly independent, you can extend it to a state or a linear functional in our case, or a linear map to the whole algebra. So if these are generators, you can extend them. And let us do the simplest possible example, so-called stationary case. In the stationary case, for example, for the simplest lattice, the one-dimensional lattice here, or I erased, but in the one-dimensional case, stationary is the same thing, let us say, this is even weaker. This is a weak form of translation invariance, very weak form in the one-dimensional lattice. So, in the one-dimensional lattice, if we have that this is constant, the expectation value of each single sum like this, I will take expectation value of this, but this will not depend on n by assumption, by the weak stationarity assumption. So it is obvious that this limit exists. So you understand that the real essence of the law of large numbers is the transition from the general polynomial to from the general monomial to polynomials, arbitrary polynomials, from the monomials of degree 1 to monomials of higher degree. So the non-linearity assumption. I want to emphasize that, you see, here you have polynomials. And you know that with polynomials, you can approximate any continuous function, at least in compact intervals or compact subsets. And then with continuous functions, you can approximate measurable functions. And when you use approximation, suppose you can do all these approximation, you see that this is a very famous notion of convergence in law. The notion of convergence in law of probability theory. So we have a kind of, the convergence in moments is not convergence in law, it's much weaker. It's convergence in law restricted to polynomial functions. And this is enough for the law of large numbers. So, as I said, this limit exists trivially because it is equal to itself, but this is non-trivial because this implies factorization. Factorization implies some independence or asymptotic independence assumption. Now, higher level. Suppose that the law of large numbers is satisfied. So we have the limit in the polynomial sense. I write limit, but you understand. N is for the net, this net of finite subset. In the following, this net will be fixed, which correspond to fixing the intervals, 0n when n varies in all possible ways. So we have the limit of, in the polynomial sense of these sums. So for the law of large numbers, we will have this kind of things. I don't put the index n because I'm summing overall n in this subset, okay? Now, suppose that this limit exists, then it will be some we will denote like this. This is, for the moment, is a pure notation. It's not a real expectation. It's a pure notation. Then we can consider the so-called, we can consider the correction of this limit as follows. Let me show you. I have written, the formula is rather long. So if I consider the mean 0, I subtract the mean to each observable. You see, this will be constant now. This, when I take the sum here, this will be a scalar, and this will be the generator. Now, I will consider this as a new sequence. And the moment central limit theorems, essentially, I know that this sequence will converge. The central limit theorem will tell you, if I define B bar, this with the zero mean sequence, what is the speed of this convergence? That is, if I multiply by some n cardinality of n to the power alpha, if I know that this limit exists, this limit exists and is identically 0, because by the law of large numbers, this limit will be identically 0. So I can ask myself, for which exponents alpha, I will have a limit for the so-called the mean 0 elements, which is non-trivial. So you see, if I multiply by alpha, this is equivalent to subtract alpha to the power 1, which is in the denominator of the law of large numbers. Okay. Let us prove the following result. The following result is true. If this limit, so the limit for the so-called the mean 0 observable, will exist and be non-trivial, not identically 0, if and only if alpha is equal 1/2. So the only normalization factor I can have in moment central limit theorem is 1/2. Why? In this case, when the normalization, the alpha is equal to 1/2, I will call these objects fluctuation observables. And these are very famous and very important in physics, are one of the fundamental objects of statistical mechanics. Let us let us see why in general case, so we will see now, I want to introduce the notion of stochastic independence. Before that, I am looking for a necessary condition for the existence of this limit. I will look a necessary condition in the weakly stationary case, when this expectation does not depend on n. It's constant on the lattice, on the set V. So you see, and I consider the expectation only of a product of two observable, which corresponds in probabilistic language to the covariance of the process. So if I have two observable, I have two normalization factors, so a factor 2 arises here. And now you have the fundamental notion of independence. You remember that in the classical probability theory, the notion of independence is well known, and if you have two random variables, x and y, defined on the same probability space, say, for example, real valued, they are independent if f expectation of fx times expectation of gy is equal expectation of fx times expectation of gy. This is the notion of classical independence. So in particular, this notion means that if I take x minus the mean value of x, this is by definition x bar, and y bar is by definition y minus the mean value of y, then I will have e x bar times y bar equal e x bar e y bar, which by definition is 0. Okay? In any case, this condition is much stronger than what we are asking that what we are asking here. We are asking only that the analog of this condition. So supposing this is true, what you conclude? What you conclude? This condition is satisfied in all. There are no exceptions. All notions of independence. In quantum probability, there are a huge number. In fact, uncountably many notions of independence. But they have all this in common. This property is always common, that it is always true. It's not true, for example, for a product of 3. But for 2 is always true. So you see, under this assumption, when I take, I want to study the limit of this sum. So this sum will factorize. It will be like this. This is the weak stationarity condition. Under the weak stationarity condition, even without supposing this factorization condition, you see, this limit is constant. The only varying factor will be this quotient. So you see that this gives 0 if alpha is less than 1/2. It will give plus or minus infinity in modulus plus infinity, if you take the norm of this object. If you take alpha greater than 1/2. And it will exist if and only if alpha is equal 1/2. So we conclude two things. That the only, as I said, the only normalization factor that you can have in moment problem is 1/2. Second, that this is a necessary condition. The existence of the limit of the covariance is necessary. Of course, if I want the limit for all polynomials, I want the limit of covariance. So it is a necessary condition. And this will be assumed in the central limit theorem. And I anticipate that is a necessary condition. Is it sufficient or not? The problem is it is sufficient, but you need some additional condition, and this is independence, what I wrote there. So the limit covariance, this will be a limit which will be depending on this 2 Bs and Bt. Remember, S and T is the index of the vector valued random variable. So the limit will be 0. If you have that the En are states, then you have Schwarz inequality. So if all these limits are 0, the limit of all moments will be 0. So you need at least one covariance non-trivial. This is well known in classical probability. So now we come, what we need? The singleton condition. Let me explain the origin of the singleton condition. The origin of the singleton condition is the following. It comes from classical probability. If I have xs, remember we have, in our case, we have a vector valued random variable with the components xs. I say that this random variable, they are defined on a certain probability space, so I have an expectation value for this joint expectation value, and the classical notion of independence is that expectation of a product is the product of expectation. So you see, it's a very simple exercise I suggest you to do, that this is equivalent to say that expectation of the product of this Fs are arbitrary Borel functions in classical probability, is equal to 0 if there exists an index S such that expectation of S is equal to 0. I have to go to to let you understand where is really the singleton condition. If you remember, we defined the non-commutative monomial. In the commutative case, a product, we can always reduce to single product because we are in a commutative algebra. But in general, we will have a function, as I wrote before, from a finite set of natural integers to the index set. Okay? And I will have a non-commutative product, for example, in the order from left to right according to the increasing order of the natural integers. I will have a product like this. The product from J from 1 to K, Fj, Fsj, Xsj. Okay. This product, in the commutative case, what it is? In the commutative case, this product will be simply a product of the form product S belongs to D, expectation, let us say, expectation of the product of, and here we will have all the products such that Sj is equal to S of Fsj, Xsj, and that's all. Okay? If the algebra is commutative, there will be many repeated indices. Okay? So by commuting the factors, I will bring them together. So this product will be a new function g. And in commutative case, I will reduce everything. Again, I change the name of this function, and I reduce to this. Okay? So in commutative case, there is no difference between these two products. But in the non-commutative case, this lets you give the meaning of singleton condition. So I will say that, remember, this notion of independence, let us call it independence, classical independence, is equivalent to, let me erase this because we have written in this way, is equivalent to what we call the singleton condition. So if there exists, this product will be equal to 0 if there exists one of the Sj, there exists an index j belonging to 1k such that Sj is different from Sh for all h different from j. So the index Sj will be the only one. It will appear in this product only one. And the function the function corresponding to this index Xsj will have 0 expectation. So, as you see, it's clear that this implies this. Because if I have this for all functions, using this formulation, I will have that because of the singleton condition, this product will contain only one factor. Okay? So when I write this as this product here will be equal to the if this condition, classical independence, is true, this product will be equal to the product for j from 1 to k of e to the product of Sj. No, sorry, the product will be S now. S belonging to D. Sj equal S, F, Sj, Xj, Sj. Okay? Now, if this product is reduced to a single index, and by assumption this expectation is 0, of course the product will be 0. So this condition implies this. The converse is also true, because I just read the proof from here to here. So the converse is very simple. If I have that this is factorized, I have a single index. I use the fact that this is 0, okay? Then what I do? It's clear, because if I have a single index, forget about this property 0. Then this will be the root of a very, very subtle distinction between singleton and strict singleton, which unfortunately is not true. So maybe it's worth if I give you the proof explicit. Okay. Huh?
Maybe you can continue next time.
Okay, let me finish this equivalence proof. Just 1 minute. Because I want to give you this proof explicitly, because later on we will have this distinction between singleton and strict singleton, which in classical probability is trivial. But in quantum is not, and there are counterexamples, and you will show. So I want to show that this condition, okay, implies this one. Let me first show that this condition in classical probability is equivalent to the following condition. If there exists a singleton so with this condition, Sj different from Sh for all h different from j, then the product over all j in this set from 1 to k, the expectation of this product of f Sj x Sj will be equal to f, let me write h here because it's a dummy index, but for intuitive reason it's better to distinguish from the singleton, which we have called j, okay? The singleton is j, and h is a dummy index in this product. So it's equivalent to say that this is equal to E of f Sj x Sj, and then I have the product, expectation of the same product, but with the h belonging to all k minus the single index j. Because of a singleton condition, there is only one with this property. Okay? So this is obvious. How do you prove this? This equivalence between this and this. Okay. Start with this which has a non-zero mean. Subtract the mean. Then you can take it without the mean outside. And then you use this property. Okay? And conversely, so what we are using that we can subtract the mean. This means that the algebra must have an identity. Because to subtract the mean means to subtract a number, which is the mean, times the identity function. Okay? But in many cases, like Boolean independence and monotone independence, the algebra is not an identity. So you cannot apply this proof. And in fact, there are counterexamples, you will see. So in the classical case, you have the three equivalents. This classical condition, this condition here that I will call strict singleton condition, which is this one, and the condition here, which is the singleton condition. They are all three equivalent. Okay? So this is the motivation to introduce this. The singleton condition in classical probability is equivalent to independence. Is equivalent. We have just proved. And what can we do in the quantum case, in the algebraic case? I'm afraid we have to see it tomorrow. Tomorrow is not Monday. Okay? And you will see that from this will not be sufficient to prove the central limit, but it will be sufficient to single out the most fundamental property of Gaussianity, which is that an expectation value of a product will be reduced to product of so-called pair partitions, to correlations. It's well known that in Gaussian measure is uniquely determined by the correlation. Correlation means product of two, expectation of product of two. So Gaussian, algebraically, the notion of Gaussianity means that an arbitrary expectation is 0 if the number of a factor in the product is odd, and is a product of pair expectations if it is even. This feature, for this feature coming from central limit, the singleton is sufficient. And this we will be next time. Okay?